Morning. Hello, I'm here today with my umbrella and my silly hat, and I'm going to explain the important role that symmetry has in understanding the Higgs mechanism. You're probably familiar with symmetry when talking about reflections, or maybe you remember from school talking about symmetry in simple shapes. For instance, a regular hexagon has 6 lines of symmetry and rotational symmetry of order 6. What we mean by symmetry here is that you can make a change, reflecting or rotating the shape, and then the result is the same as the shape you started with. Let's use a more algebraic example. Here are 2 equations, y equals x and y equals x squared. Now graphically, they look like this. Now, if we make the change, x goes to negative x, which is the same as reflecting in the y-axis, this is the result. Now in the first case, we've changed the resulting graph. However, in the second case, we get the same graph that we started with. So, we would say y equals x squared is symmetric under this transformation. This kind of transformation is called parity, and whilst it is important for particle physics, there are many other kinds of transformations that we're interested in that are much more mathematically complicated. In fact, symmetry is so important for particle physics, they named a whole magazine after it. So why are we interested in symmetries? Well, the reason is because of something called Noether's theorem, named after Emmy Noether, who proved it in 1915. Now, she was described by Albert Einstein as a significant creative mathematical genius, which is a pretty good compliment coming from him. In very simple terms, Noether's theorem says that if there's a symmetry in a system, then there must be a conserved quantity. And in fact, Noether's theorem gives us the tools to find what that conserved quantity is. Let's take a simple example. When writing equations, we often need to choose the centre of our coordinate system, or, as Dr. Sheldon Cooper would put it,
would be 0, 0, 0, 0.
Now, it might make sense for us to choose this to be the centre of our coordinates, but I could just as well move here and make this the centre of our coordinates. The universe still works in the same way. Apples still fall to the ground, hot coffee still goes cold, and custard is still objectively the most delicious substance on the planet. So, if the universe obeys this spatial symmetry, Noether's theorem gives us the tools to find a conserved quantity, and in this case, that conserved quantity is momentum. Similarly, rotational invariance leads to angular momentum conservation, and time translational invariance leads to energy conservation. Now at school and university, we make a big deal out of momentum and energy conservation, and so now you know why these quantities are conserved. Earlier, I said that Noether's theorem concerns symmetries of a system. To be more accurate, we would describe a system using something called a Lagrangian. You can think of a Lagrangian as a kind of formula that contains all the types of energy in a system and how those are related. In quantum field theory, we use Lagrangians that contain all of the particles, or quantum fields, in the universe, as well as how those fields interact. The standard model Lagrangian is so important you can even get it on a t-shirt. So I still haven't explained what symmetries have to do with particle physics. Well, to do this, I'm going to show you some maths. Now, remember our deal, don't panic. Here is a Lagrangian. Psi is the electron field, and m is the electron mass. Don't worry about what all of the other squiggles mean for now. Now we want to know if this Lagrangian is invariant under a kind of transformation called a local U1 gauge transformation. The maths here is actually quite similar to the phase that we talked about in the last video. Unfortunately, if we make this transformation, we end up with an extra bit, an extra term in our Lagrangian. However, if we were to add an extra field to our theory, let's call it A, and if we were to give this field its own special transformation properties, we can cancel out that extra term and make it so that our Lagrangian does obey the symmetry. Now the great thing is, this extra field that we've added perfectly describes a fundamental particle, the photon. It also describes how that photon interacts with our electron. In fact, we've just derived the very basics of quantum electrodynamics, or QED, for which these three chaps were awarded the Nobel Prize in 1965. QED is our current best understanding of how the electromagnetic force works. So this strategy of looking for symmetries, then adding fields to maintain the symmetry, and thereby describing fundamental forces using those fields, is a pretty successful strategy. It also worked for the nuclear strong force, which predicted a particle called the gluon, which was then discovered. And a similar process was used to describe the nuclear weak force, which predicted the W and Z bosons. But here we hit a problem. In physics, we actually quite like it when something unexpected happens. It means there's something new to discover and learn. But there's a mystery here. You see, all of the particles that we've added up until now have had zero mass. They're massless. But the W and Z bosons, when they were discovered, were the heaviest particles we'd ever found. Now, you may say, why is this a problem? Why can't we just add a mass to our Lagrangian? But the problem here is that would break the symmetry that we've worked so hard to keep. Now, what we need is a way for our equations to remain symmetric, but for results that are not symmetric. That's why I'm here with my umbrella. Now, if I place the umbrella upright, there's a rotational symmetry here, because there's no one preferred direction. If I place the umbrella on the ground, now there's no rotational symmetry, because there is one special direction. What if I don't choose the direction though? What if I just let the umbrella fall? Well, the result is the same symmetry breaking. Why does the umbrella fall? If you said gravity, that's right. As physicists, we would say that this has a lower gravitational potential energy than this. So the system changes to find the lowest potential energy state. This is what we mean by spontaneous symmetry breaking. We started out with a symmetry, and because the system is looking to find the lowest potential energy state, the symmetry is spontaneously broken. And now we're ready to talk about the Higgs mechanism. Technically, it's called electroweak symmetry breaking, and there are many people who should be credited with developing it, including Engler, Brew, Guralnick, Hagen, Kibble, and of course Higgs. But for me, it's just easier to call it the Higgs mechanism. The Higgs mechanism proposes a new field of nature, the Higgs field. Now, this field is quite different from the other fields we've talked about so far, but we won't go into the details. Now, if this Higgs field interacts with the other particles, slowing them down, that could explain why they have mass. Remember how we said that we needed equations that are symmetric, but results where that symmetry is broken? Well, to see how this works in the Higgs mechanism, let's look at the potential energy of the Higgs field. Now, from its shape, it gets its nickname, which is the Mexican hat potential. And that's why I'm wearing this sombrero in such a ridiculous environment. Now, the way to understand this as a graph is that the horizontal position is the value of the Higgs field, and the vertical height is the corresponding potential energy. Now hopefully you can see this has a similar symmetry to the umbrella from before. So what happens if we let the field change from 0, it falls to the lowest potential energy state, and the symmetry is broken. Now, when you do this mathematically, you get extra terms in the equation, the Lagrangian, that look just like the mass terms that we needed. But how can we prove that this is more than just a nice theory, and this is actually how the universe works? If we count the number of degrees of freedom, we find the Higgs field has 4 degrees of freedom. Now the W+, W-, and Z bosons all get their mass through the Higgs mechanism, which leaves 1 degree of freedom left. Now, this degree of freedom corresponds to excitations of the Higgs field. Just as the photon is the quantized excitation of the electromagnetic field, the Higgs field is quantized into Higgs boson particles. If we can make and detect these Higgs boson particles, we can prove that the Higgs field exists and that our description of the universe using symmetry is still a good description. So to recap, we talked about how important symmetries are in modern physics. We looked at why and how symmetries are broken, and how the Higgs mechanism works to give gauge bosons mass. And finally, we said that if the Higgs field exists, we can prove it by finding the Higgs boson particle. So how do we make and detect these particles? Well, that's a topic for the next few videos, but for now, thanks so much for watching. Let me know in the comments your thoughts and questions, and until next time, it's goodbye from me. Goodbye.